For most of its history, physics advanced by observing what could be measured. Objects were tracked, forces were calculated, and reality appeared increasingly precise as instruments improved. The universe seemed willing to reveal itself, layer by layer, as long as the right questions were asked. But eventually, physics reached a point where observation was no longer enough. The equations still worked, but the reality they described could no longer be seen. This is where string theory appears, not as a discovery, but as a response to a failure. Modern physics rests on two extraordinarily successful frameworks. Quantum mechanics describes the behavior of particles with astonishing accuracy. General relativity describes gravity and the structure of space-time with equal precision. Each theory works perfectly in its own domain, yet when both are applied together at the deepest levels of realita, mathematics collapses. The equations break. The universe refuses to be described. String theory emerges from this fracture. It is not an experimental observation, but a mathematical necessity. A structure invented not because it was seen, but because without it, the equations cannot continue. At the heart of string theory is a simple but radical idea. What we call particles may not be point-like objects at all. Instead, they may be tiny, vibrating strings. These strings are unimaginably small, far beyond anything current technology could ever detect. Their vibrations determine the properties we associate with particles: mass, charge, spin. Different vibrations appear as different particles, not because they are separate things, but because they are different expressions of the same underlying structure. This idea is not poetic. It is mathematical. When physicists replace point particles with one-dimensional strings, many of the infinities that destroy quantum gravity calculations disappear. The equations stabilize. Gravity, which stubbornly refuses to fit into quantum theory, suddenly finds a place. A graviton, elusive quantum of gravity appears, naturally within the framework. Not added by hand, not assumed. It simply emerges. Yet this elegance comes at a cost. String theory does not describe a universe like the one we see. In order for its equations to work, reality must have more dimensions than the 4 we experience. Not 5 or 6, but 10, sometimes 11. These extra dimensions are not extended like space. They are compact, folded into shapes so small they remain invisible. Reality, in this view, is far more intricate than perception allows. Here, physics enters unfamiliar territory. The theory works mathematically, but it cannot currently be tested. The energies required to observe strings directly are far beyond what any conceivable experiment could achieve. String theory predicts no single, unique universe, but an enormous landscape of possible universes, each with different physical laws, each mathematically consistent. This raises an uncomfortable question. What does it mean for a theory to be real if it cannot be observed? Physics has always relied on experiment as its anchor. A theory survives only if nature agrees. String theory, however, exists in a space where experimental confirmation may never arrive. It is a structure of pure consistency, held together by logic rather than evidence. It describes how reality could be, not necessarily how it is. This does not make string theory false, but it changes its meaning. Instead of being a description of nature, it becomes a description of the limits of description. It shows how far mathematics can be pushed before observation disappears. It marks a boundary where physics stops pointing outward and begins reflecting inward toward the structures of thought, language, and abstraction. In T-Sensei, string theory is less about what reality is made of and more about how reality resists being reduced to objects. If the fundamental constituents of the universe are not particles, but vibrations in invisible dimensions, then solidity is an illusion of scale. What appears stable exists only because deeper complexity averages into simplicity. This idea quietly echoes something found through inner observation. Experience, too, appears solid only at certain scales. Thoughts feel real until they are examined. Identity feels fixed until attention slows down. Beneath appearances, processes replace objects. Patterns replace things. What seemed fundamental dissolves into movement. String theory does not claim that reality is vibration in a mystical sense. It does not say the universe is music or harmony. It says that what we perceive as matter may arise from something far less intuitive, something that cannot be pictured, only calculated. Reality becomes less visual and more relational, less object-like and more structural. This shift is deeply unsettling to the human mind. We are shaped to trust what we can see. We believe what can be pointed to. String theory offers nothing to point at. It exists entirely within equations. It survives, not because it is observed, but because it refuses to contradict itself. This leads to a profound tension. Physics seeks truth through observation. Mathematics seeks truth through consistency. String theory sits between them, belonging fully to neither. It is physically motivated, but mathematically sustained. It may describe reality, or it may describe only the boundaries of our models, and yet its existence matters. It tells us that reality may not be accessible in the way we expect, that the deepest layers of existence might never become visible. That knowledge does not always converge toward clarity. Sometimes it converges toward silence. The failure to test string theory is not merely a technical problem. It is a philosophical one. It asks whether reality must be observable to be real, whether explanation must be grounded in experience to be meaningful, whether understanding is the same as knowing. In this way, string theory becomes a mirror. It reflects not only the structure of the universe, but the structure of human inquiry. It reveals how far we can go before the tools we trust, measurement, observation, visualization, no longer apply. What remains when physics can no longer see? What remains is humility. String theory does not offer comfort. It does not offer certainty. It does not promise a final answer. It stands as a reminder that reality may be deeper than any description we can build, that the universe does not owe us visibility, that understanding may end before existence does, and when explanation falls silent, something else becomes noticeable. Not a conclusion, not a model, but present. The fact that reality is happening at all, regardless of whether it can be captured. The fact that experience unfolds even when knowledge pauses. The fact that something exists even when it cannot be fully said. String theory does not tell us what the universe is. It tells us where our explanations begin to fail. And in that failure, a deeper attention becomes possible. Still, within